Hello everyone, and welcome to the video for section 10.1 on sequences and series. Most of you are probably seeing this video at the conclusion of spring break, so I hope you did have a great break. Some of you are maybe watching this beforehand, so I hope you're enjoying your break and everybody is coming back well rested and ready to go. Anyway, our skill objectives for this particular video are: 1. Find the terms of a sequence when given a general term. Number 2, look for patterns to find the general term of a sequence. Number 3, apply factorial notation. Number 4, apply recursion formulas. Number 5, use summation notation to represent a series. And number 6, evaluate a series. Conceptual objectives on this one is understand the difference between a sequence and a series. And number 2, understand the difference between a finite series and an infinite series. Let's start out with a definition of a sequence. A sequence is a function whose domain is a set of positive integers. The function values or terms of that sequence are going to be written with subscript notation. So you'll have a sub 1, a sub 2, a sub 3, and that pattern will continue a sub n and just continue on. Now, if you have a finite sequence, the domain is going to be a finite set of numbers. So it's going to go from 1 to n. If it's an infinite sequence, then the domain is all positive integers. Now, a couple of things you also need to keep in mind here. A sub n, that term is often called the general term. And it will be written as in terms of n, because that's what you're plugging values into that general term to create that sequence. Another thing that you have on this is that often when we deal with these general terms or when we're working with these, it might be more helpful to, instead of starting with a sub 1, a sub 2, a sub 3, it might be more helpful to start as a sub 0, a sub 1, a sub 2, like that. So that is an option as you progress through. But for the most part, when you're asked to work with this, we will start it with 1. So that will be the first value. There are really two things that you're going to need to do with a sequence. Number 1, you're going to have to identify the terms from a general term. And this is going to be done by putting positive integers into that general term. The general term, again, will be written in terms of the letter n. That is our variable. And so we're going to plug positive integers in for n in the general term, and that will help us identify terms of that sequence. The other thing that we'll be asked to do is identify the general term from a sequence. So in this case, what you're going to have to do is you're going to have to identify and generalize patterns that you might notice in the terms of that sequence to help you create that general term. Let's take a look at a couple examples here, 4 examples actually, in terms of finding where we have to find the first 4 terms. Now, again, what this means is that when they do this, they're going to tell you that they want you to start with 1, and so you're going to plug in 1 in for n. So when I want to find a sub 1 in the first one, in that first problem, I want to find a sub 1. A sub 1 is going to be 3 times 1 minus 4. And when I do that, I'll get negative 1. A sub 2 is going to be 3 times 2 minus 4. And the result there is going to be 6 minus 4 will be 2. And I can just continue that on. I can get a sub 3. A sub 3 is going to come out to be 5 when I take 3 times 3 minus 4. And a sub 4 is going to come out to be 3 times 4 minus 4 is 12 minus 4, which would be 8. So those would be the first 4 terms of this particular sequence. Now this one's that first one was not so horrible. I mean, you're just plugging it into one spot. But that can change. We can do our sequence, our general term, can have all sorts of different forms. In this next one, you'll notice that it's a fraction. So I have it's n over n squared plus 1. And so when I plug 1 in for n, so I get a sub 1 is going to be 1 over 1 squared plus 1, so I'll get 1/2. a sub 2 is going to be 2 over the 2 squared plus 1. So I'll get 2 over 5. And then a sub 3, in this case, is going to be 3 over the 3 squared plus 1, so it'll be 3 over 10. And a sub 4 comes out to be 4 over 17. Another thing that you're going to notice on these is in some cases you will see the general term have something like we see here where we have a negative 1 to a power. What that does is that's looking, when you see that, you know that the terms of the sequence are going to alternate between positive and negative. And so in this case, when I find a sub 1 in this case is going to be negative 1 to the first over 3 to the 1 minus 1, which is 0 power. So that's going to come out to be negative 1 over 1, so I get negative 1. A sub 2 is going to be negative 1 to the second over 3 to the 2 minus 1 power. Well, negative 1 to the second is going to be positive, so I'm going to get a positive 1/3. A sub 3, because now the exponent on negative 1 will be negative, or be an odd. I know this is going to be a negative value, and it's when I put 3 in for n, I'm going to end up with negative 1/9. And a sub 4, when I put 4 in for n, I'm going to get a positive 1 over 27. What I'd like you to do right now is pause the video, and I would like you to identify the first 4 terms of our last sequence. So in this case, the sequence is negative 1 to the n plus 1 power over n squared. So pause the video, identify the first 4 terms, and when we come back, we'll talk about what you came up with. Welcome back. On this one, you should have come up with a sub 1 is equal to 1. A sub 2 will be negative 1/4. A sub 3 will be 1/9. And a sub 4 will be negative 1/16. Now, if you did not come up with those, take a moment right now to go and write this out, showing the substitution, and then simplify it from there. Remember, if you have a negative 1 to an even power, it's going to be positive. A negative 1 to an odd power is going to be negative. If you are not able to go and identify any corrections that need to be made, make sure to note that so that we can talk about it in class as well. Now let's look at some examples in terms of finding the general term. In this first example that we have, which we have the sequence of numbers there, 3, 6, 9, 12, 15, and so forth. One of the things that I notice on that one, I think you probably have noticed it too, is that each one of these values here is a multiple of 3. So I can say that in this sequence, the 3 is really 3 times 1, 6 is 3 times 2, 9 is 3 times 3, 12 is 3 times 4, and 15 is 3 times 5. So when we look at this, with this pattern, we notice that it's going to be 3 times. In the first term, it was 3 times 1. The second term is 3 times 2. So I'm looking at this as a sub n is going to be 3 times n as my general term. I'm taking 3 times whatever the term number is to get each term of the sequence. In the second one, a couple things I noticed. Number one, I noticed that it is alternating. So I know I'm going to involve negative 1 to a power. And because it's the odd terms that are negative, I know in this case that a sub n is going to involve negative 1 to the n. I just have to figure out what's happening with the rest of it. Now, what I can do with this, and often this is helpful, is to write every term as a fraction. So like that negative 1, I'm going to write that as negative 1 over 1, then I have 1 over 4, and then negative 1 over 9, then 1 over 16, and negative 1 over 25. And the next thing I notice on here is that my denominators are perfect squares. This is negative 1 over 1 squared, and then that's 1 over 2 squared. Negative 1/9 is negative 1 over 3 squared. 1/16 is 1 over 4 squared. And negative 1 over 25 is negative 1 over 5 squared. And so we'll notice that it is the term number. The first term, the denominator is 1 squared. In the second term, the denominator is 2 squared. Third term, it's 3 squared. So I know, looking at this, that this is really going to be negative 1 to the n times 1 over n squared. Or if I want, I could say it's a sub n is negative 1 to the n divided by n squared. That would be my... So if I write these now as powers of 2, I will have 1 over 2 to the first. The second term is going to be 1 over 2 squared. Third one is going to be 1 over 2 to the third. And the fourth term is 1 over 2 to the fourth. And so I can see the pattern here is that what's changing is the power on 2. And so in this case, a sub n is going to be 1 over 2 to the n power. Now, another pattern that we're going to look at is what's called factorial notation. Now, some of you have experience with this, some of you may not. And really what happens on this is that we have a positive, n is going to be a positive integer, and you're going to see it's the notation with the exclamation point, and that's read n factorial. And this is the product of all positive integers from n down to 1. So in this case, the way the book defines it, n factorial is going to be n times n minus 1 times n minus 2, and times that pattern continues down to 3 times 2 times 1. And the book talks about this being when n is greater than or equal to 2. They also define 2 other factorials to make up the gap. Number 1 is 1 factorial is equal to 1, which makes sense. 1, it would just be 1 times 1. And then the last one is 0 factorial. Now, 0 factorial is defined as 1, and it actually, there's patterns and stuff that require that to happen. Every year I look at this, I need to remember to go and look up and see if there's another more proof of that. But it is really just a consequence of patterns that it definitely happens that way, and so it has been defined as that way. So if you even put 0 factorial in your calculator, it will come up to be 1. And so what you have with this, when I look at that, 0 factorial is 1, 1 factorial is 1, 2 factorial is going to be 2 times 1, which will be 2. 3 factorial will be 3 times 2 times 1, which equals 6. 4 factorial is 4 times 3 times 2 times 1, which is 24. And 5 factorial is 120. What I'd like you to do right now is take a moment, and I'd like you to go and calculate 6 factorial and 7 factorial. Now, welcome back. Now, as you were working on these, as you looked at these, I was hoping you would also notice that when I found things like 4 factorial, could also be thought of as 4 times 3 factorial. And 5 factorial could be 5 times 4 factorial. So I have 5 times 24 would give me 120. So therefore, 6 factorial can be thought of as 6 times 5 factorial. And when you did that one, you should have got that 6 factorial is 720. And so 7 factorial would just be 7 times 6 factorial. So that would equal 7 times 720. And when you multiply that out, you will get 5040. So that's what you should have come up with. Now let's take a look at some examples of calculations you're going to have to work with these factorial problems. Now, one of the things you're going to have is just like we saw before, finding the first 4 terms of a sequence. So in this case, what I have, it's a sequence that does involve a power of x, and you'll notice that the denominator is a factorial. So a sub n in this case is x to the n plus 1 over n minus 1 factorial. And so on this one, the first term, again, we'll let n equal 1. So a sub 1 is going to be x to the 1 plus 1 over 1 minus 1 factorial, which comes out to be x squared over 0 factorial, which we know is 1. A sub 2 is going to be x to the 2 plus 1 power over 2 minus 1 factorial, which that comes out to be x cubed over 2 minus 1 factorial is 1 factorial, which is also 1. A sub 3 is going to be x to the 3 plus 1 power over 3 minus 1 factorial. And so that comes out to be x to the 4th over 2 factorial, which is 2. And a sub 4 in this case is going to come out to be x to the 4 plus 1, which is 5, over 4 minus 1 factorial would be 3 factorial, which we know is 6. So our first 4 terms of this particular sequence are those listed: x squared, x cubed, x to the 4th over 2, and x to the 5th over 6. Another thing that they're going to ask you to do is simplify expressions involving factorial. Now, we had the next two, you'll see one involves numbers and the other involves letters, involves n. And we're going to be asked to simplify both of these. Now, a couple of things you have to be aware of here. A common mistake that students make: they see 5 factorial times 2 factorial, and they think, oh, that's just going to be 10 factorial. No, you cannot multiply those like that because it's very, very different. 10 factorial, which we have in the numerator, is equal to 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And so that's going to be over 5 factorial, which will be 5 times 4 times 3 times 2 times 1, multiplied by 2 factorial, which is going to be times 2 times 1. So what we have here, this part right there, that's 5 factorial. This part right there is the 2 factorial. And at this point now, we can simplify this. Well, the first thing I notice on here is in the denominator, the 5 factorial, those are the same as all these values here will cancel out these values there. And now what I have, the 2 will go into 6 3 times. And so the end result right now is that this whole fraction is really equal to 10 times 9 times 8 times 7 times 3. And so I can just put that into my calculator, and I find that that is 15,120. Please notice, though, again, how we've been able to go and reduce that problem with the numerical values in there. Now, the next thing you have in number 3, we want to go and simplify this expression, the n plus 2 factorial over n factorial. Now, here's the thing you have to remember. When you look at the numerator and denominator in terms of this, one of these is actually going to be bigger than the other. In this case, n plus 2 factorial is going to be bigger than n factorial. And so therefore, I know n factorial is actually a factor of n plus 2 factorial, just like 5 factorial was a factor of 10 factorial up above. And so I can go and write that out. I can write out that n plus 2 factorial over n factorial. I can say that is equal to n plus 2, using the definition of a factorial, how it just reduces by 1, n plus 2 times n plus 1 times n factorial over n factorial. And now that reduces out. And so my final answer in this case is n plus 2 times n plus 1. And you can multiply that out if you want, but I'm just going to leave it in that form. Now, again, at this point, please take a look at each one of these examples. Make sure that you are comfortable with everything that I did in them. And if you are not, be sure to note that and make sure to ask about that in our next class. Now, so far, every sequence that we've dealt with, we've had a general term, which allowed us to go and calculate the term, the specific term number by plugging in a value for n. So if I wanted the 7th term, I could put 7 in for n. If I wanted the 20th term, I could put 20 in for n. Some sequences, though, we do have what's called a recursive definition for that sequence. And what that means, a recursive definition, is really one that you build the sequence from previous terms. So when you look at this definition, you're going to see a couple of things. Number one, that you're going to be told the first term or terms. You might be told multiple terms, but you'll definitely be given at least the first term of the sequence. There'll also be a recursion formula. That's going to be where it's going to say a sub n is equal to something, but this time instead of being in terms of n, it's going to be in terms of some a sub n minus 1, a sub n minus 2. It'll be in terms of the specific terms, the terms of the sequence, not the term number. And then what you're going to do is you're going to build that sequence, the terms of that sequence, off of each previous term. So let's take a look at a couple examples. Now, in the first one that we see in blue, I'm told a sub 1 is 4, and a sub n is 2 times a sub n minus 1 here. So this means, this is like saying that my next term is it's the previous term, 2 times the previous term minus 1. So in this case, when I want a sub 2, when I put 2 in for n, I know a sub 2 is going to be 2 times a sub 2 minus 1. Well, in this case, a sub 2 minus 1 is 1, so that's going to be 2 times 4 minus 1, which comes out to be 7. I can then calculate a sub 3 using the same method. A sub 3 is going to be 2 times a sub 3 minus 1. So that's going to be 2 times a sub 3 minus 1 is 2, so a sub 2 in this case was 7, so it's 2 times 7 minus 1, which will give me 13. And I can continue doing this. If I want to do a sub 4, a sub 4 is going to be 2 times 13 minus 1, which will come out to be 25. And then a sub 5 is going to be 2 times the 25 minus 1, which would come out to be 49. And I can keep building that sequence in that way. Let's look at another example. In this next one, we are told a sub 1 is 1, and this time a sub n is a sub n minus 1 over n factorial. So you'll see both the n and the a sub n. But the fact, because of our numerator here being a specific term of the sequence, this is a recursive definition of that sequence. And so, if I want the second term, I know a sub 2 is going to be a sub 2 minus 1, which will be a sub 1 over 2 factorial, which is going to be 1 over 2, which is 1/2. And then a sub 3 is going to be a sub n minus 1, so a sub 2 over 3 factorial, which comes out to be 1/2 divided by 6, which, remember, dividing by 6 is the same as multiplying by 1/6, so it's 1/2 times 1/6, which equals 1 over 12. And I can continue this pattern as I go. A sub 4 is going to be 1 over 12 divided by 4 factorial, which is 24. So it's going to be 1 over 12 times 1 over 24, which if you multiply those, you're going to get, that's going to come out to be 1 over 288. And so that would be my fourth term of that sequence. Now, some recursive definitions are easier to use. I would say that this first one here was probably easier to use than this one because of the calculations we had. But both definitions do have an issue in that if you want, unlike the general term, where if I wanted the 10th term, I could put 10 in for n and get that 10th term. In the recursive definition, if you want to know what the 10th term is, you have to know what the 9th term is because it's going to be built. The 10th term is going to be found by applying some calculation to that 9th term. And if you're going to know the 9th term, you have to know the 8th. If you're going to know the 8th, you have to know the 7th, and so forth. So you can see there's the issue you have with the recursive definition, The general term is going to be probably our most common one used, but the recursive definition does come up a lot. In fact, there are some sequences that just have it's easier to work with the recursive definition. Now let's take a look at a couple other definitions. And now we're going to move, we've done all these things with the different sequences, now we're going to move to series. And what a series is really, it's the sum of the terms of a sequence. So, first that we have is the definition that we have here. The sum of all the terms of an infinite sequence is called an infinite series and is denoted by this right here. A sub 1 plus A sub 2 plus A sub 3 plus ... plus A sub n plus, and that just continues on. Now, when we work with these, you'll also, some of you may have some experience with this, we also have what's called sigma notation on this. And the way sigma notation works is it's a shorthand for writing this. And so this would be equal to, you'll see the Greek letter capital sigma, it looks like that. There's an index, and the index, we're going to say n equals 1. And since this is an infinite sequence, it's going to be 1 to infinity of whatever A sub n is, the terms of that sequence. The next thing we have is what's called the finite series, or the nth partial sum. The sum of the first n terms of a sequence is called the finite series, or nth partial sum, and is denoted by S sub n equal to A sub 1 plus A sub 2 plus A sub 3 plus ... down to whatever A sub n is. Now that also has a sigma notation that would be equal to the sum, and this time we'll use a different letter. We'll use I equals 1 to n, because we had the final was n, of A sub I. And so that would just be our sequence of the sum, that partial sum, the sum of the first n terms of the sequence. Here's some examples of partial sums, and they're going to ask you to find these partial sums. What happens here in the first one, I have that we're taking the sum as n goes from 1 to 4 of 3n plus 1. So I'm going to go through, plug in the values of n. So when I plug 1 in for n, 3 times 1 plus 1 is going to be 4. Plus, when I plug 2 in for n, I get 3 times 2, which is 6, plus 1, which is 7. Then when I plug 3 in for n, I get 3 times 3 plus 1, which is going to be 10. And when I put 4 in for n, I get 12 plus 1, which is 13. And so I add those up. 4 plus 7 is 11, plus 10 is 21, plus 13 is 34. So that partial sum is equal to 34. In the next one, I'm taking the sum as n equals 0 to 4 of 4 factorial. Now notice, again, our index of summation, where we're starting it, doesn't have to necessarily be 1. So in this case, they're going to start it at 0. And so I know this is going to be 0 factorial plus 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial, which we know that's 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, and 4 factorial is going to be 24. So when we add those up, 1 plus 1 is 2, plus 2 is 4, plus 6 is 10, plus the 24, that equals 34. Now let's look at this last one. In this case, n is going from 2 to 5. So in this case, we start out with 2, and when I plug 2 in, I'm going to get negative 1 to the second times 2 squared plus negative 1 to the third times 2 to the times 3 to the squared plus negative 1 to the fourth times 4 squared plus negative 1 to the fifth times 5 squared. So when I do that, negative 1 squared is 1 times 2 squared is going to be 4. Now the next one is going to be minus 9 plus 16 minus 25. And so I do these calculations. I come up, I'd say 4 minus 9 is negative 5, plus 16 comes out to be positive 11, minus 25 comes out to be negative 14. So the sum of this part, that finite series, is negative 14. There are also sums of infinite series. We can do those as well. I will do an example of that in class, but there is also, if you would like to see an example of that, that can be found on page 1026 of your textbook. It is example 8 in section 10.1. Now the other thing you're going to be asked to do is you're going to be asked to write a series using the sigma notation. So in this case, what I have in the first two, these are infinite series. So we'll start it at 1, and it will go up to infinity. But what happens on this, when you want to write it as an infinite series, what you have to do is you still have to identify your pattern. You have to think of the terms of the series as a sequence itself. So we have to find that general term of that, and that's going to be what we're going to put after our sigma sign. So in this case, when I look at these values here, I notice that I have 8, 27, 64, and 125. And one of the things that I notice on there is that 8 happens to be equal to 2 to the third power. And I know 27 is 3 to the third, and 64 is 4 to the third, and 125 is 5 to the third. And so when I look at this, in my first term, I had 2 to the third. My second term was 3 to the third. My third term was 4 to the third. My fifth term is, my fourth term is 5 to the third. I notice that a sub n in this case is n plus 1 to the third power. So my summation notation on this one, my sigma notation, is going to be, this is going to be the sum, n equals 1 to infinity, of n plus 1 to the third power. Please keep in mind that this is also, I started it with n equal to 1, but I very well could have just gone and said that this was also equal to the sum as n equals 2 to infinity of n to the third. That would also give me the exact same sequence. So either one of those works. And again, you have the freedom to choose how you're going to start your summation, what the lower limit of that summation is going to be. In the next one, I know a couple different things when I look at this one. Again, we have to identify that pattern, and I notice on this that I am alternating between positive and negative terms, and so therefore in this particular one, I know a sub n is going to involve negative 1 to a power. Now because it's my even terms, my second and fourth and sixth term that would end up being negative, I know that my exponent is going to be n plus 1. Because the only way I'm going to get a negative value is if I'm taking negative 1 to an odd power. So in order to make my negative 1 when n is an even number, to make it an odd power, I have to add the 1. Now the next thing I look at is my fractions. And I notice on here, I'm going to write that as 1 over 1. And I look at my denominators, I have 1, 2, 6, 24, and 120. So I look at that and say, wait a second, I do remember those terms. That sequence of values. That happens to be the factorial notation. So in this case, that would be, in terms of this, that's when n is, in my first term, I have 1 factorial. In my second term, I have 2 factorial. My third term is 3 factorial. So I know that's going to be 1 over n factorial. And so the summation on this is going to be the sum as n equals 1 to infinity. I can write that as negative 1 to the n plus 1 over n factorial. The next one here in number 3, notice I don't have the dot, dot, dot. This is a finite sum. And so I've got to go and determine what my sequence is going to be. So I want to determine that nth term and then make sure I plug things in appropriately so that I can get my summation, so I get the terms I have there. Now again, what I notice when I look at this is that these happen to be powers of 2. So in this, 4 is 2 to the second, plus 8 is 2 to the third, plus 2 to the fourth, plus 2 to the fifth, plus 2 to the sixth. And so when I do this, I can really choose how I want to start this. If I could go through and say, well, I noticed that my exponents go from 2 up through 6, so I could write this as the sum as n equals 2 to 6 of 2 to the n. That works. I could also use the idea that, well, when my first term was, when n was 1, I get 2 to the second. When n is 2, I get 2 to the third. So I could also look at that as a sub n equals 2 to the n plus 1, in which case then that sequence, if I wrote it in the summation, that would be the sum as n equals 1 to 5 of 2 to the n plus 1. Again, I will leave it up to you as which way you choose to write that sequence, but realize that there are many different ways that I can write the series in terms of with the summation, where it starts, where my lower limit, my lower summation limit, and that upper summation limit, where they start and end. With this, I will now conclude this video. Again, I hope that you are either having a great break or that you had a great break, and we will see you in our next class, which for A days will be Monday, I want to say 13th, or B days will be Tuesday the 14th. So we will see you then.